All right, so today I'm going to continue where I left off last time. I'm going to be talking about projections and least squares today. So I'll start with just kind of a brief reminder on some of the things that we talked about regarding projections. So let's say that W is a subspace of some Rn. And then let's say that we have like a vector B. So B is just some vector in Rn. And I had this kind of a visual last time where W, I'll draw it as if it were a plane in this picture. And then we have a vector B, and it's not necessarily in W. It could be, but generally speaking, B would be outside of W, so I'll draw it like that. So then the projection of B onto the subspace W would be represented by this red vector that I've just drawn, which I was denoting as a vector P last time. So this vector P represents the projection of vector B onto the subspace W. And there's like maybe different notations that you could use for this. Here I might use the notation like projection of B onto W. Or I could also maybe like write out like projection of B onto W as well. So there's maybe two different notations that I might be switching back and forth between. Okay. And there were kind of two important properties of this projection vector. So the first property of this projection vector that is worth noting is that amongst all of the vectors in W, this projection vector P is the vector that is like closest to vector B among all the other vectors in W. Okay. So that's one of the key properties of the projection. So among all vectors in W, this projection vector is the one that is closest to vector B. Okay. And the second important property was if we look at the vector connecting from P to B, whoa, okay. So that vector there, that was referred to as the error vector. And it's equal to the difference B minus P. Yeah. So this error vector makes a right angle with the subspace W. So you can see that this error vector, oh, well, is orthogonal to the subspace W. More precisely, you can say it's orthogonal to every vector in W. Okay. Now I went over the special case where W was a line. So I'm not going to go through all of it again, but I'll just kind of remind you, we came up with a formula for the projection of a vector B onto a line. So the formula depended on choosing a vector A that lies along the line. And then we had this formula that the projection was equal to A dot B over over A dot A times vector A, okay? All right. So this was a formula for projecting vector B onto the line spanned by vector A, okay? And today I'm going to go over the general formula for projection. So like if you want to project B onto any subspace, not necessarily a line, we'll go over the formula for that. Now before I get to that formula though, there's something else that I want to talk about first, which is another one of the applications. All right, 1 second. All right, so let me start by talking about what least squares is. Okay. So least squares is an application of projections. Last time I went over Graham-Schmidt, which is another application of projections. And this time I'm going to talk about least squares. So here's kind of the setup of what least squares is about. So let's say that we have an equation, ax equals b. And let's say that we know that this equation has no solution, okay? So if there's no solution, yeah, no, I know, yeah, I saw as well. Yeah, no, yeah. So if there's a no solution, uh, sometimes what we want to do is we want to find kind of like what would come closest to being a solution to this equation. And that is what least squares is all about, okay? So for least squares, what we want to do is we want to find a vector. Oh, huh. I think it's about to go away again, though. Yeah, we'll see, yeah. So we want to find a vector that comes closest to solving this equation. Okay. So like maybe why would we want to do this? So it may be that we expect this equation to have a solution, but maybe like the numbers in the equation come from measurements and like some kind of an experiment. Yeah, so there could be like errors in those measurement numbers, which leads to having no solution. But like you kind of expect there should be a solution, so you still want to try to solve it, kind of, okay? So uh, let me kind of draw a picture to kind of illustrate what's going on. So since this equation has no solution, something that we've kind of talked about quite a few times before is that for this equation to have no solution, that means that the vector b is not a linear combination of the columns of A. So in other words, you can see that vector b is not in the column space of A. Okay. Because if b was in the column space of A, then there would be a solution. Okay. So since there's no solution, we can say b is not in the column space. So we have a picture that looks something like this, where let's say this plane represents the column space of A. And we have a vector b, which is not in the column space, so it's sticking out of it instead. All right, so maybe you guys could kind of see where this might be going. So whereas it's not possible to solve ax equals b because b is not in the column space, the closest we can get to vector b in the column space would have been its projection vector p. Okay. So in a sense, then the closest we can get to solving the equation ax equals b is to instead solve the equation AX equals P, where P is the projection of B onto the column space of A. Okay? Now this equation here is going to have a solution because P is in the column space of A. And the idea is that P is the closest that we can get on the right-hand side to vector B. So solving this equation, AX equals P, should give us something that gets close to solving AX equals B. That's kind of the idea of this, okay? Okay. So a solution to this equation, AX equals P, is going to be called a least squares solution. To the original equation AX equals B. Okay. Yeah, what was that? Yeah. So the idea is we're gonna try to solve this equation AX equals P as opposed to AX equals B. Because we can solve AX equals P since P is in the column space. And in a sense, that's kind of like the closest equation to AX equals B that we can solve because P is the vector in the column space closest to B, okay? All right, now just a little bit of notation. So a least squares solution is, at least in this class, it's commonly denoted as X with a hat on top of it. So I guess like if you see this notation X hat in the context of least squares or projection, it refers to like the least square solution. Okay. All right, now in order to find a least square solution, it turns out that we can solve for the least square solution without solving this equation directly. Okay. So we haven't actually talked about how to compute projections in general just yet. So at first glance, it looks like you wouldn't be able to solve AX equals P without knowing what the projection vector is. But there's kind of a clever way around that. So I'll kind of explain how that works. So the key is that if we go back to the picture and if we look at the error vector, which we've been talking about quite a bit as well. Okay. The error vector we know is orthogonal, in this case, to the column space of A. And since this error vector is orthogonal to the column space, we've learned that the orthogonal complement of the column space is the left null space. So to say that the error vector is orthogonal to the column space is to say that the error vector is in the left null space, or the null space of A transpose. Okay. So then that means that if we take A transpose times the error vector, that should produce 0, because that's what it means for to be in the null space of a matrix. So what I'm going to do here is two things. So substitute into this equation the error vector E was equal to B minus P. Okay. All right, and then with the idea that x hat, the least square solution, would be a solution to ax equals p, so that a times x hat should equal the projection vector. What I'm going to do next is, in this equation, I'm going to replace p with a x hat. So that will leave us with a transpose times b minus a x hat equals 0. And then here, what I'm going to do is I'm just going to distribute the A transpose and rearrange the equation a little bit. So what you should get is A transpose A x hat must be equal to A transpose B. Okay? So here we have like another equation that we can use to solve for the least square solution. So we can use this equation instead of using the equation ax hat equals p. Okay. So that's convenient because in this equation here, you would have to compute the projection vector first in order to try to calculate the least square solution. But when you look at this equation here that we have, it's purely in terms of A and B, which would have been like given from like the original equation. So this equation here is going to be more convenient and easier to work with to try to find the least square solution. This equation that I've kind of boxed here is sometimes referred to as the normal equations. Okay. So I don't know if you guys hear that terminology. Yeah, if you guys hear the terminology normal equations, it refers to this equation here, A transpose A times x hat equals A transpose B. Okay? Yeah. All right, so yeah, I'll get the projector looked at sometime this week, I guess. So we'll see if we can get it fixed. Yeah, yeah. All right. Yeah, I'm not sure what if it's like the bulb that's an issue or something else. Yeah. Okay. So I'd like to try to maybe do some examples of finding the least square solution. So I'll try and do 2 examples in particular. So I guess one of the applications of least squares comes in the form of curve fitting. So like given a set of points, you want to try to find a curve that will like sort of best fit those points that you're given. So let's consider the following example first. Let's say that we're given the following data points. And I'll arrange the points into a table. So we have the point negative 1, 0, 0, 1, 1, 1, and 2, 3. Okay. And I guess not super important for the problem, but I'll get a little bit of a sketch going. So here we got like the point -1, 0, 0, 1, 1, 1, and 2, 3. Okay. And in this example, what I'm going to be doing is we're going to calculate the line that will kind of best fit these 4 points. All right, so let's see how we could do that using these squares. Okay. Now we know that the equation of a line can be written in the form like y equals mx plus b, you know, where m is the slope and b is the y-intercept. Okay. So what I'm going to do first is I'm going to take the 4 data points that are given, and I'm just going to plug them into the equation of a line, so plug them in for x and y. So for the first point, when x is -1, y is equal to 0. So plugging that in for x and y gives us this equation. Next, if I plug in 0 for x and 1 for y, we get that equation there. Likewise, I'll plug in 1 for x and y. And lastly, I'll plug in the point 2, 3. And that will give us 3 equals 2m plus b. Okay. Well, so we have a system of equations, but I guess what's happening though is there's actually going to be no solution instead. And the reason why there would be no solution to the system of equations is because there is no line that would pass through all 4 of these points. Okay. So first, let me take the system of equations and let me set it up in the form like a x equals b. Okay. So here in the system of equations, m and b would have been the 2 unknowns. The coefficients are -1, 1, 0, 1, 1, 1, and 2, 1. And then on the other side, we have a 0, 1, 1, 3. So that would be like the vector b. Okay. And then as I kind of commented on just now, this system of equations would have no solution. Since there is no line that passes through all 4 points. So in order to find the equation of the line of best fit, the idea is we'll get the least squares solution to the system of equations instead. Okay. Because if the equation has no solution, then the next best thing we could kind of do is to get the least square solution. That's the idea. So to get the least square solution, we're going to look at this system of equations instead. Okay. All right, so in order to do that, we'll first need to compute A transpose times A. We'll also need to compute A transpose times B. So I'll do that over here right now. So we're going to do A transpose times A. So first here is A transpose. Then I'm going to multiply with A. So if we multiply all of that out, let's see, it's going to be 1 plus 0 plus 1 plus 4. Negative 1 plus 0 plus 1 plus 2. This will be 2 again. And then we're going to get 4 at the end. Okay, so that's A transpose A. Next, I also want to do A transpose times B. So here's A transpose, and then B was 0, 1, 1, 3. Okay. So let's multiply all that out. We're going to get 0, 0, 1, 6, so 7. And 0, 1, 1, 3, so 5. Okay. So then this equation that we were trying to solve, explicitly this equation is 6224 times x hat equal to A transpose B, which was 7 and 5. Okay. So in order to solve this equation, and I guess x hat, let's maybe write it like this perhaps. So x hat would contain the slope and the intercept for the line of best fit. So maybe I'll denote that as m hat and b hat, so slope and intercept if you will. Okay. So we want to solve this equation now for the m hat and the b hat. It's a 2x2 system, so you could easily solve it by doing elimination. Since it's a 2x2 system though, I think what I'll do is I will compute x hat as being equal to the inverse of this matrix times 7, 5. Okay. And I guess the reason why I'm gonna do it this way is because I remember a formula for the inverse of a 2x2 matrix. Okay. So I'll write the formula here kind of off to the side. So if you had a 2x2 matrix ABCD, the formula for its inverse, it was 1 over AD minus BC times DA minus B minus C, like that. Okay. Okay. So just because I know that formula, I'm going to solve this by using the inverse. So it's going to be 1 over, so AD would be 6 times 4, minus BC, so minus 4. And then we swap the diagonal, so 4 and 6. And then we change the sign of the off-diagonal entries like that. Okay. So we have that times 7, 5. And let me go ahead and just finish multiplying this out. So we have 1 over 20, and then we're going to get 28 minus 10. so that's 18. And then we're going to get negative 14 plus 30 is 16. Okay. So I guess if I multiply the 1 over 20 inside, we'll get 18 over 20, which we could say is 9 over 10. And then I guess 16 over 20 would be 8 over 10, or 4/5. But maybe I'll leave it as 8/10, because it might be nice to have a common denominator, I feel like. Okay. So then this gave us the slope and the intercept for the line of best fit. So then if I plug this into the y equals mx plus b formula, the line of best fit is going to be y equals slope is 9/10, and then the y-intercept was 8/10. Okay. Sure, that's a good question. So that's true, yeah. Yeah, so line of best fit, I haven't actually defined it too well. So I guess for starters, there could be more than one line of best fit because it depends on how you measure like one line fitting better than another. Okay. A little bit right now, yeah. I can elaborate on it in just a couple of minutes though. But yeah, so there's more than one way to measure how well a line will fit through a set of points. And depending on how you measure it, you could actually have a different notion of what the best fit line would be, okay? But here, the best fit line that we're calculating is the one that we calculate by doing this process of getting the least square solution, okay? I can actually talk about why we call it least square solution, because that ties into your question of in what sense is it the line that's best fitting our points, okay? But one thing that I want to talk about first, just before I get to that. So in this example, I calculated this line of best fit. There's maybe a question of like how can we measure like how good of a fit this line actually is. So one way to get some sense as to how good this line might be fitting the points is to calculate the error vector from the least square solution. So I guess like to measure how good of a fit this is, one way of doing that is to look at the error vector. Okay. So let me just do that for this example. So remember the error vector was b minus p, okay? All right, and well, maybe skipping ahead a little bit here, but and then remember that the projection vector p was equal to a times the least square solution x hat. Okay. Because remember that's how the least square solution was defined. X hat was defined to be a solution to like ax hat equals p. Okay. So if I want to compute the error vector in this particular example, so let me scroll back up real quick. Let's see, the vector B was 0, 1, 1, 3. So that's B. Oh, whoops, and I want to do minus. And then I'm going to take A, so negative 1, 0, 1, 2, 1, 1, 1, 1. I'm going to multiply that with the least squares solution, which was 9/10 and 8/10. Okay. Okay, so let's just see what the error vector ends up being. So I guess first I will multiply out A times x hat. So that's going to be negative 9/10 plus 8/10, so negative 1/10. We'll get 0 plus 8/10 for the first one. So we had negative 1 times 9/10. Okay, yeah, no problem. That's your, yeah, that's right, that's right. Right, right. Oh, yeah, so the next one would be 9/10 plus 8/10, so 17 out of 10. And the last one is 18 plus 8, so 26 over 10, okay? And then let me kind of do the subtraction here to finish this calculation. So the error vector would be the 0 minus the negative, so it's 1/10. 1 minus 8/10 is 2/10. 1 minus 17 over 10, that's negative 7 over 10. And then lastly, 3 minus 26 over 10 would be 4 over 10. So that would be the error vector. And what might be of interest is to calculate the magnitude of the error vector to get a sense for like how large the error is, okay? So if I calculate the magnitude of the error vector now, so that would be square root of 1/10 squared plus 2/10 squared plus negative 7 over 10 squared, and finally plus 4 over 10 all squared. And let me just also compute this real quick. So I think it's 1 plus 5 plus 49, 55 plus 16. So I think it's the square root of 61 over 100, if I did that right. Okay. So then here the magnitude or the size or the length of the error vector, that kind of gets you like a sense for how large the error was and getting the least square solution to solve the original equation, okay? Okay, so let me go ahead and talk just a little bit about, so in what sense is this line that we got by doing least squares, in what sense is it the line of best fit? So that actually ties into, I guess, why we call it the least square solution as well. All right, so yeah, so in what sense is the line obtained from least squares the line of quote unquote best fit? Okay. All right. So Let me draw a picture. So just sort of as an example, let's say we had some data points. Okay. And let's see here. Let me draw kind of like a line passing through those points. Okay. Yeah. Now let's say that the y components of these 3 points are y1 for this first point. Let's say y2 for the second point. And then y3 for that third point. Okay. And then here, let me mark these 3 corresponding points on this line. So let's say for this first point here that its y coordinate is y1 hat. Likewise for this second point here, let's say that its y coordinate is y2 hat. And for this third point here, let's say that its y coordinate is y3 hat. Okay. So let me extend this further down. Okay. One way of measuring how far this line sort of deviates from the given data points. So one way to measure that is to take the difference between the y values. So we're going to take the difference between the y values at the points and the corresponding y values like on the line. What we're going to do is we're going to take the difference and we're going to square it to make it positive. And then we're going to add the sum of all of that up. Well, we're going to sum all of it up to get like a sense for what the total like a deviation of the line from the data points would be. So what the least squares solution is actually doing is it's actually picking the line that will minimize this sort of sum of squares of the differences. Okay. So the least squares line that we're computing, if you will, minimizes this sum of squares of differences. Okay. Okay. So that's the sense in which the least squares line is the line of best fit. It would be the line that minimizes that quantity there. Okay. But if you choose another measure of how a line deviates from some given points, you could come up with a different line of best fit. But we won't consider those, at least not in this class, I would say. Okay. All right. Cool. Now let's see here. So let me kind of do like another example. So I want to do just another curve fitting example, at least kind of setting it up. Maybe for the sake of time, I won't work it out completely though. But let me go back to the same 4 data points that I used in the last example. And in the last example, what we did was we found like the line that would best fit these data points. So this time I want to alter it slightly, and let's say that we want to find a parabola now that will best fit these points instead of a line, okay? So in order to do that, it'll be similar to what we did in the last example. Okay. So a parabola would be described by a quadratic equation. So you could maybe set it up as like y equals like maybe a plus bx plus cx squared. Okay. So that will kind of represent the equation of a parabola. And what I'm going to do is I'm going to plug in the 4 data points that we have for x and y. So we plug in the first point, so y is 0, x is -1. When we plug in the second point, y is 1, and we're plugging in 0 for x. The third point, x and y are both 1. And then lastly, y is 3 and x is 2. So that's going to leave you with those 4 equations once you plug in the 4 points. And then, just as before, I'll convert this into a sort of a ax equals b form. Okay. So here we have 3 unknowns, a, b, c. The coefficients were 1, -1, 1 from the first equation, 1, 0, 0 from the second equation, 1, 1, 1, and 1, 2, 9. Okay. And then on the other side, we had 0, 1, 1, 3 for B. Okay. All right, now, so again, we can sort of presume that there would be no solution to this system of equations since there is no parabola that passes through the 4 points. So to get the parabola of best fit, what we're going to do is we're just going to find the least squares solution instead. Okay. So then remember the least square solution, we're going to compute it by doing this equation A transpose A times x hat equals A transpose B. Okay. So here we'll have to compute A transpose A. So let me set that up right now. Here's A transpose. And then times A. Okay. Okay, so let me kind of work this out real quick. So that's going to be 4. I think that's going to be 4. No, that's going to be 3. And then next, 1, 0, 2. That's 11. These would be 3 and 11. 1, 0, 1, 4. And that's going to be 6 there. The next one, -1, 0, 1, 18. And the last one is going to be 1, 0, 1, and 81. So 83. So if I multiplied everything out correctly, I think that would be A transpose A. I'll make a small comment that whenever you compute A transpose times A, that is going to be, it's going to end up being a symmetric matrix. Okay. So you might have noticed as I was doing my computation, once I figured out the 3 and the 11, I just kind of immediately filled these in as well. And that's kind of because I knew that the result was going to be symmetric. Okay. And the same with the 18. Okay. All right, now let's see here. I would also need to compute A transpose B as well. So let's do that one next. B3. So I'll also just quickly do this computation. So I think that's going to be 5. I think that's 7. And then I think the last one is 29. Okay. Oh no, that'll be 28 rather. So something didn't see. Okay. Okay. So assuming I made no mistakes, that's A transpose A and A transpose B. So then this time when we're solving for like the best fit parabola, we ended up with like a 3x3 system now, as opposed to a 2x2 system. So that's A transpose A. X hat would contain like the coefficients of the equation of the parabola of best fit. So I'll call them A hat, B hat, and C hat instead of the original ABC. And then A transpose B we have as 5, 7, and 28. Okay. Okay, now last time in the previous example, I used the inverse of A here to get the least squares solution. But that was because the inverse of a 2x2 is pretty simple. We have this formula for it. There isn't a formula that's as simple for a 3x3 inverse. So in this case, instead of using the inverse, I would maybe try to solve it by doing elimination instead. So therefore, I would sort of set up the augmented matrix. For that system. And then I would do elimination to try to solve for the A hat, B hat, and C hat, okay? So for the sake of time, I think I'm not gonna work through that. But I'll just at least say like at this point, you would do elimination. At least to upper triangular form so that you could then back substitute. Once you figure out the A hat, B hat, and C hat, then the equation of the parabola of best fit. So the general equation was like y equals a plus bx plus cx squared. And you're just going to plug in what you found for a hat, b hat, and c hat for like the ABC, the coefficients, okay? All right. So let's go ahead and end the review by going back to the main topic of projections. Okay. Okay. So uh, one of the reasons why I wanted to talk about least squares first is because it kind of helps us get a formula for computing projections in general. Okay. So we can quickly recall what we did just now with least squares. Uh, so the least square solution x hat satisfies two equations. Ax hat equals p, the projection vector, and also A transpose A x hat equals A transpose B. Okay. And then as a sort of additional reminder, when we were talking about least squares, let's kind of emphasize that P was specifically the projection of vector B onto the column space of A. Okay. So the idea is you can compute the projection vector by first getting the least square solution. So if you solve for x hat in the equation A transpose A x hat equals A transpose B, and then once you solve for the least square solution, you can just take what you found for x hat and multiply it by A, and that product would then give you the projection vector. Okay? All right. And I kind of secretly did that in the first example when I was computing the error vector. If you maybe go back and see, look at that, I actually kind of already did this. Now, if A transpose A, if this matrix is invertible, then in theory, this first equation here could be solved by just multiplying A transpose A inverse to the other side of the equation. So I did that in the first example when I was finding the line of best fit. I could have done that in the second one as well, but it was a bit messy, so it would have been easier to do elimination instead. Okay. But in theory, if A transpose A is invertible, you can compute the least square solution using this formula. So now if I sort of take this and just multiply all of it by A on the left, so A times x hat, which is all of this. Okay. This kind of huge product that you have here should equal the projection vector. And specifically, it was the projection onto the column space of A of the vector B. Okay. Okay, so a couple of things. So this product of matrices here, A times A transpose A inverse, and then times A transpose. That product, we call it the projection matrix. Maybe projection matrix for the column space of A, okay? Because what this matrix does is it multiplies with a vector B, and then it outputs the projection of B onto the column space of A, okay? So in a problem that's like asking you to compute like a projection matrix, it would basically be asking you to compute this product, okay? And then this is all somewhat specific though to projecting onto a column space of a matrix. So if we want to ask sort of like a more general question, let's say that we have, back to the original premise that I started with, let's just say you have a subspace W of Rn, and then you have, vector B again, and you want to find the projection of B onto W. So let me use this notation. So projection onto W of vector B. What you can do is you can start by finding a basis for the subspace W. Okay. And then take those basis vectors that you found and put them into a matrix A as its columns. So by doing this, the idea is if you put the basis vectors of W into the columns of A, then the column space of A would be equal to the subspace W. And therefore, you can use the formula that we found for projection onto a column space to then project onto W, okay? Okay. All right, so I'll maybe do just one example to end the review. Okay. I'll make a quick comment and then I'll begin the example. So to compute the projection vector, the idea is to get the least square solution. Once you get the least square solution, just multiply it with A to get the projection, okay? If A transpose A is invertible, then you can use this formula specifically to calculate the projection. And so this might be nice to do, especially if A transpose A ends up being like, say, something small like a 2 by 2. But in the event that A transpose A was like 3 by 3 or larger, you maybe don't want to find its inverse. So you do always have the option of just solving this equation via elimination instead of using the inverse. And then once you have the least square solution, again, just multiply by a to get the projection vector. Okay. So like you're not necessarily forced to use this formula to compute the projection. If you like want to avoid computing the inverse of A transpose A, then instead you always have the option of doing elimination to get the least square solution, and then multiplying by A afterwards. Okay. So I'm just going to do one example, and then we'll probably wrap up with that. So let's say that we're given some matrix A. Maybe I'll keep it a little bit small. Okay. And then let's say we're given some vector B. And in this example, what I want to do is I want to find the projection of this vector B onto the null space of this matrix A. Okay. Okay. So what I'll need to do first is I'll need to find a basis for the null space of A. Okay. So that'll be kind of the first step of solving this problem. So remember that to find the basis for the null space of a matrix, your strategy is to row reduce. Okay. So here I made the matrix pretty small, so if we just do row 2 minus 2 of row 1, let me see what that will give us. That'll be 2, that's going to be 5. Okay. So this would be the reduced row echelon form of A. Okay. And then I want to convert this like into a system of equations. So say from the first row, we get the equation 1x1 minus x3 minus 2x4, and we set it equal to 0 when we're looking for the null space. The second row gives us x2 plus 2x3 plus 5x4, again equals 0 for null space. And I guess you want to get like your special solutions to get the basis for the null space. So the way that I do that is I parameterize the free variables. So x3 and x4 would be free in this case. We could say x2 is negative 2s minus 5t. And we could say x1 is going to be 1s plus 2t. Okay. And I guess if we just take the coefficients of s and then the coefficients of t, so these two vectors would give us a basis for the null space. Okay. So now that I have a basis for the null space of A, I'm going to create a new matrix, and I guess I have to call it something other than A, so I'll call it B. So I'm going to take the basis for the null space of A and just put them into a new matrix B as its columns. Okay. So now what was that? So let's see. So these equations, what happened was, so x3 and x4 were free. So that's why I just called them S and T. To get this part over here for x1 and x2, I kind of like move these over to the other side. Okay, all right, great. So we took the basis for the null space of A. They became the columns of the matrix B over here. So like the column space of B would be the null space of A, okay? And then we have this formula for projecting onto column space, okay? So projection onto the column space of B, a vector B. Let me maybe set up this formula for that computation. So I want to do B times B transpose B inverse times B transpose, and then times vector B, okay? Okay, so I'm just gonna finish up with all of these computations here. So first is, let's compute B transpose times B. So B transpose is 1, -2, 1, 0, 2, -5, 0, 1 times B. So I'll work this out. 1 plus 4 plus 1, 2 plus 10, 4 plus 25 plus 1, it's 30. Okay. All right, so that's B transpose B. Let's go ahead and just compute the inverse of that real quick. 2 by 2, so I can use the 2 by 2 inverse formula. So A times D is 180 minus B times C, so minus 144. I interchange the diagonal entries, and then I change the sign of the off diagonal entries to get the inverse. Let's do a little bit of simplification. I can cancel out a 6 from everything. Okay. So then I guess next, I just want to take a B, compute all of this now. So let's see, we have B transpose B inverse. Let's just write it all out. So here's B times B transpose B inverse times B transpose. And then I want to multiply with vector B at the end as well. B was originally 1, 2, 3, 4. Okay. So let's see here. Let me multiply these two together, and let me multiply these two together. So if we multiply these two first, it'll be 5 minus 4, negative 2 plus 2, negative 10 plus 10, 4 minus 5, 5, negative 2, negative 2, 1. I think that's what you get there. And then when I multiply these two together, we're going to get 1 minus 4 plus 3, 2 minus 10 plus 4, like that. Okay. And then I'll just finish by multiplying these out. So it'll be 1/6 and then 0, 4, 8, negative 4. Or if I just cancel out a 2 from everything, 0, 2, 4, negative 2. Like that. Okay. So then this vector here that we got should be the projection of vector B onto the null space of A. Okay. And I guess I'll end my example with that.